Hello everyone, this is Team A Firefighting Robots final project deliverable. My name is Daniel Choi.
My name is Cassidy Jones.
Hello, my name is Alexander Alatriste, and I'm responsible for the Aerial Incident Response Robot.
Good evening, everybody. This is Matt Davis. I am a mechanical engineer.
Today I am going to do our introduction. So I'm going to start with our problem statement. Our problem statement is we are developing a solution to provide increased firefighting capabilities and reduce the risk to firefighters. So our firefighting robots can't replace the humans in firefighting, but they can reduce the fire station's response time by 20%. Our robot system will assist firefighters in putting out fires, rescuing people, um, letting the firefighters know where they can enter in safely, where the people are to help them get out. So our direct and indirect customers of our firefighting robots will primarily be our firefighters, including the military firefighters. But it won't only just impact the firefighters around the world, it will impact everyone else too, the public, researchers, and things like that. To develop a swarm of robots for disasters, we will need people to continuously put research in to make sure that we stay with the technology, that we're constantly getting faster, we're constantly helping out the firefighters and things like that. We'll need the public support, recommendations on what could have been done better whenever things happened, when a fire happened in their building area, wherever the case may be, so we can help continuously advance our technology. So we have 6 design requirements for our firefighting robots. So the first one is the system shall reduce fire station's response time. The system shall withstand up to 1100 degrees Fahrenheit. The system shall identify potential structural weaknesses and obstacles. The system shall provide real-time data. The robot shall not be damaged or operationally affected. And the system shall provide medical evacuation. The creators of these robots are Alexander Altriste. He is doing the aerial incident response robot. The robot will have the ability to respond quickly to fires, emergency situations. Cassidy Jones, who is doing the probe robot, which will be dispatched inside structural fires to gather real-time data regarding the integrity of the building. Daniel Choi, the firefighting robot. The firefighting robot will help assist firefighters in putting out fires. And Matt Davis with the Medevac robot, which will help load and evacuate any casualties.
So here is the Aerial Incident Response mechanical design. From the bottom view, what you can see are wheels and a sensor. That sensor's functionality is to determine the altitude of the aerial incident response robot. From the side view, what you can see are cameras that also serve as sensors. These are the thermal imaging cameras. They also function as a sensor. And then you have propellers at the top that allow the robot to fly and reach whatever potential altitudes they might need to reach. And then from the top view, what you can see is a DC motor, a battery, and an emergency battery as a backup, just in case the primary battery does fail. The circuit design, what you can see is an ultrasonic distance sensor. We're going to be using that. That is the sensor that was on the bottom of the air robot, which determines the altitude. So that sensor will constantly be taking reads. It is controlled by an Arduino board that is hooked up to a motor, which are connected to the propellers, and a 9-volt battery. It's very ambitious for a 9-volt battery. And next you can see my flowchart and code for the flying portion of the air robot. So the aerial incident response robot is manually taken off of a docking station, which is 4 feet above the ground, and from there it will begin to fly because it is in a constant loop. of asking if the altitude is greater than 48 inches, where if it is above 48 inches or 4 feet, that must mean that the mission is ongoing to continue to fly. And if it is below that altitude, then the mission must be complete and the air robot is clear for landing. And so for here, you see my code. We have a loop there that essentially is just changing the outputs of the motor determined on the if statement. And that completes my presentation for the aerial incident response robot.
So this is my robot, the Probe robot. The Probe robot, as you can see in the front here, is a camera to have real-time data to show the structural scene of the building. The antennas on top to transmit that data, make sure it's constantly going in real time. And at the bottom and the top are little micro sensors, which will help the robot make sure it is dodging all flying debris and it's not getting knocked over, it's not running into buildings. So here's my circuit design for my firefighting robot. So on the left here is for the circuit design for it to avoid the flying debris, and on the right is for the camera's stream or recording. So for the drone monitoring, which is avoiding the debris, as I like to call it, here is a flow chart here. And so they'll start, this code goes with this flow chart. So when you start, it'll basically ask it, is debris falling? Yes, continue to move forward, and then start over. And continue, ask that question. Is debris falling? No. And it'll go slow down, delay a little bit. And in the front, is the front distance less than 20 inches? Yes, move backward, and then continue to start over. If no, then continue to start over.
Firefighting robot receives fire location data from first incident response robot and travels to that location and provides fire suppression. To the rear, there's fire hose fitting where fire hose can be connected from which the water flows. To the rear, there's a camera that is a primary means of navigation using computer vision. There are also 3 ultrasonic distance sensors that measure distance from robot to surrounding objects, and depending on the distance, it turns left or right to avoid collisions. Rotating assembly allows the nozzle to rotate both horizontally and vertically depending on the location of the fire relative to the robot. There are 2 major circuit components. Collision avoidance system incorporates 3 sensors, and depending on the distances they measure, they control 2 motors that drive tracks. And rotating assembly, I incorporated 2 servo motors that change the direction at which the nozzle is directed to accurately hit the fire. For collision avoidance system, it first measures the front distance. If front distance is greater than 20 inches and continues moving forward. Otherwise, it compares the right distance and left distance, and whichever is greater, it will turn towards that direction. Rotating assembly, it first determines whether or not the fire is within reachable distance based on the distance from the fire and the height at which the fire is located. If it is within reachable distance, it will stop moving. Otherwise, it will move closer to the fire. Here's a quick demo of collision avoidance circuit. If the front distance is greater than 20 inches, it will continue moving forward. As you can see, both motors are moving. And when front distance is less than 20, it will measure the distance of left and right, and whichever one is greater, that's where the robot is going to turn. So if the distance is greater on the right side, then the left motor will keep turning to turn right. And if the left distance is greater, then the right motor will continue running to turn left. For rotating assembly, one on the bottom is vertical servo and one on the right is the horizontal servo. Horizontal servo receives data from the bearing, and bearing is determined by the GPS or compass. That's the relative direction of fire from the robot, and that value is just going to be inputted directly to that servo. And for vertical servo, it's going to receive ground distance and fire height data from incident response robot, and it's going to calculate the appropriate angle using the projectile motion of water. If angle is invalid, then that means the robot is too far away from the fire to reach. On the other hand, if the angle is valid, then that means it's within the reach. That's when it's going to stop and change the vertical angle to that angle.
First, we're going to start by looking over the mechanical design. As you can see, here's a kind of going to be a flexible gurney style robot. The main material will be made out of a durable plastic fabric. Then, as you can see here, there are three main components to it. The hinge point, as you can see here on the left, is going to be a pivot point in the robot. It's allowed to traverse more technical terrains, even possibly staircases. After that, you're going to go down to the tank track here. Again, this adds to its versatility and flexibility going over rough terrains, depending on what you may encounter. Again, aid in helping climb staircases and anything of the like. And then on each four sides, front and left and right, you're going to have an ultrasonic distance sensor. This will actually enable it to better navigate itself around obstacles or navigate internal buildings. This is just kind of going to be the overall flow chart. We'll get into the detail when we get to the coding, but basically its main instinct is going to be for it to move front, and if it is anything further than 4 or 5 inches away from any kind of wall or anything blocking it, it should continue to move forward. If it encounters anything, it will begin to lead its sensors to the front, left, and right. And this is some of the circuit design that is tied to our medevac robot. As you can see, there are 4 distance sensors at the front, back, left, and right side. Right now, it's only coded for the front, left, and right. Hopefully, with some software updates in the future, we can include that rear sensor, but it's already wired for it. That'll aid it to be able to go in reverse on its own or a mirror action when needed. So that potential firefighter could just flip it into a kind of a mirrored prototype, and it would just reverse its functions and basically turn that rear one into the front one. But for now, that one's not operational, but we went ahead and included it into the design for whenever we get the software updated. Outside the sensors, we have an Arduino board, a 9-volt battery, and 2 DC motors are the main components of this circuit. This is just a quick overview of some of the coding going on. Basically, it's got its pins and the output set up for all the sensors. Even the rear is already kind of programmed, at least from the lingo of it, even though it's not actually in the functional programming at the time. But again, that rear sensor is already part of it and ready to go for whenever the software updates are available. But basically, the quick overview of this coding is it's going to be constantly searching for the front distance and to make sure that our left and right distance is equal to each other, keeping it in the center path of wherever it's going. And then again, as long as that front sensor does not detect anything within 5 inches of it, it'll continue to move forward.
The robots are intended to work together during firefighting missions. This mission begins with the Aerial Incident Response Robot, or AIR for short, arriving to the incident. The Aerial Incident Response Robot will then begin taking and analyzing thermal images. Once that data is collected, it is shared amongst the other robots. Next follows the more important aspects of the mission. AIR will establish a connection with the firefighting robot. AIR will then ask the firefighting bot if the fire is still present. If the fire is still present, it will wait until the firefighting robot sends data that states the fire has been extinguished. When the fire has been extinguished, AIR will establish a connection with the drone probot. Next, AIR will ask the drone probot if there are casualties present. If not, AIR will begin to compile all of the data and send an after-action report to the authorities. If casualties are present, AIR will establish a connection with the medevac robot. The medevac robot will receive the coordinates for casualties. AIR will ask medevac if all the casualties have been rescued. If there are still casualties that need to be rescued, AIR will resend the coordinates of the remaining casualties. If all the casualties have been rescued, AIR will begin to compile all of the data and send an after-action report to the authorities.
Hello everybody again, it's Matt Davis again. Just kind of go over some other more details about our robots and the team concept that we've developed here. Our individual robot base models will basically be around $125,000 at a starting point. but each robot will have an upgrade package available for an increased price. For example, consumers pay for the higher grade batteries with increased life, higher output, and reduced charging times. That's just one example of some of the luxury packages or higher options that consumers can go for. The entire team of robots price point will be $400,000. With this, that will also include the communication software linking all robots together. And just like the individual price points, the price can increase depending on the upgrade packages that the consumer purchased at the time. So there are some, currently there are some individual firefighting robots on the market, but we are the first to implement a team of robots to aid in the rescue by addressing specific needs in the field. For example, our Drone Probe robot will be the first of its kind. It will be dispatched to the scene before sending in any personnel. It'll be able to gather data about the scene and relaying information about the fire, structural integrity of any buildings, and number of casualties back to our command centers. Then the firefighter robot is superior to any of its competitors. The stability and maneuverability will allow it to minimize exposure to firefighters on the ground. And its adaptable water delivery system allows it to adjust delivery angles to navigate through windows or openings to areas that it cannot get to based on its mobility. The drone incident robot is our team's overwatching eye in the sky. It'll provide live data about the scene and any potential changes or risks going on at the scene. Again, this can be relayed back to the command center, to the incident commander, and give him the information he needs to make some real-time decisions to get his people out of there or reposition personnel or resources to a different area. And lastly, not but least, our medevac robot will be the last on scene, but don't underestimate it. Its strength and mobility will minimize the amount of manual power needed to receive casualties from the scene, and also aid in getting them out safely and comfortably. This is a key component. It takes a lot of manpower to move individual patients. Our medevac robot will do a lot of the heavy lifting for our firefighters. And that's all I have. Again, my name is Matt Davis, and I will be standing by for any questions at the end of our presentation. Thank you.
In summary, our system's overall objective is to assess and assist. The first incident response robot and probing robot collect detailed information about the incident and communicate information to the incident commanders so that the commander can make the most informed decisions, while firefighting robot and medevac robot physically assist the firefighters in putting out fires and evacuating casualties. We believe that our system as a whole will significantly reduce the rescue response time, minimize the workload and risk associated with firefighting. Looking back, if we could do this project again, we will find another problem that requires creative solution, and we'll start the project earlier as we slightly ran out of time toward the end. We've identified two lessons. First is engineering design process. Exposure to the engineering design process helped us understand how to systematically create solutions and how to select a solution that aligns with the customer needs in a quantitative and qualitative manner. The second lesson is teamwork. Humanity has accumulated enormous amount of knowledge in the past centuries, and science and engineering have become so technical that you will never be able to finish a project by yourself. So in that context, modern engineering solutions inevitably require interdisciplinary collaboration. Being able to work as a team is a critical skill that is absolutely necessary for any engineers. So it was an extremely valuable experience to work as a team and collaborate with other students.